evening, everyone. Welcome to the March 2017 edition of our Big Bear Valley Astronomical Society virtual lecture series. I know you're tired of me hearing me say how excited I am for the lecture we have this evening. I say that a lot, but every month it's true. And this evening is far from a exception in that. We're very fortunate to have this evening's speaker. Back when I was an undergraduate, I won't say exactly when that was, but one of the big questions in astronomy at the time was how common are planets? And we really had no real evidence of whether they were common or very rare. A lot of people were claiming that you couldn't get, most stars couldn't form planets, certainly not multiple star systems. And a lot of people are saying, well, maybe 1 in 10 planets, 1 in 10 stars had a planet. Wild, crazy optimists said, maybe since a lot of these stars probably are going to have planetary systems like ours, maybe there's almost as many planets in this galaxy as there are stars. Well, over the past couple decades, we've really started to answer that question. And over the last few years, we really started to learn how filthy our galaxy is with planets. And that is really due to the success and results of the Kepler probe from NASA and the follow-on now K2. This evening's speaker is a primary on that program. We're very fortunate to have him. Since I've been very disorganized today, I haven't had a chance to really put together an intro, so I'm going to read directly from the bio he sent me. Steve Howell works for NASA and was very recently, up until very recently, the scientist in charge of the planet-hunting Kepler mission and the scientific brains behind the still operational K2 mission. Steve is now the head of the Space Sciences and Astrobiology Division at NASA Ames Research Center. He received his PhD in astrophysics at the University of Amsterdam and has over 900 scientific publications spanning many wavelength regimes, performing research on variable stars, instrumentation, spectroscopy, and exoplanets. Steve has written or contributed to numerous scientific textbooks, and his textbooks on digital imaging detectors, CCDs, is a standard in college courses around the world. And I know at least a couple of us here in the room have that book. He's a frequently invited speaker at scientific conferences and public forums. Steve enjoys sharing science and astronomy with people everywhere, and apparently that includes Big Bear. Following up on A Kepler's Dozen, a book many of you now have in front of you, Steve is pleased to have once again teamed up with Dave Summers put together Kepler's Cowboy, which a lot of you also have in front of you. A romping ride through outer space. I really like this bio. He lives in San Francisco Bay Area with his partner Sally and enjoys scientific challenges, the great outdoors, vegetarian gourmet cooking, and playing blues music. And yes, he still considers Pluto a planet. Please join me in welcoming Dr. Howell.
Well, and with that, the light and the electricity quit. Wow, that's pretty impressive. Hi, folks. It's so nice to see you, and thanks for inviting me along. I spoke to some of you, and amazingly, almost 3 years ago, I can't believe it, I was looking at the talk I gave at the conference there in Big Bear in May of 2014. I can't believe it's been that long. So thanks for having me back. So I didn't want to duplicate what I talked about then for 2 reasons. One is it was a few years ago, and the other reason is that I thought you would want to hear about some different things, but I will talk about exoplanets. I don't think you can have a talk today, especially if you've been involved with Kepler, that doesn't involve exoplanets. So you have to click there. Okay, let me go to the next slide. Everybody okay with that? We're moving along?
Yep.
Yep, okay, good. So this is a sort of a standard slide that once you go to NASA headquarters in Washington, D.C., or you get into management, you show this because you want to put people in a perspective of what's called a roadmap. And this is a roadmap of the exoplanet missions and the exoplanet telescopes that NASA is using to get to one of their goals. And one of their big goals is, can we detect some signature of life somewhere else in our galaxy or in our universe? So a number of these space telescopes and ground-based telescopes really exist. You certainly have heard about Hubble and Spitzer and Kepler and K2. Those are the three space telescopes here that are NASA space telescopes that exist. The other sort of line here that starts with CoRo and goes through Gaia, those are telescopes that the European Space Agency, the Europe version of NASA, has put into space. And then the next missions for NASA will be TASS and JWST up to WFIRST, and the Europeans will go to CHIOPS and Plato. Those are all basically in the works right now. There's pieces of hardware sitting in clean rooms in various places around the United States and the world for those telescopes. And the final space telescope here, which you see those two lines kind of joined together, which is the hopeful joining of budgets from Europe and from the United States as well, because the New Worlds telescope, which it'll change its name by the time it gets built, is going to be the largest telescope ever launched, and it's going to have a sole purpose, and that is to actually get direct images of planets that orbit other stars. So some of you may be young enough to be around when the New Worlds telescope actually gets launched and does that. Some of us may be seeing it in our retirement or something like that. Telescopes on the ground that are used are the Keck telescopes on Mauna Kea in Hawaii. They're the two twin 10-meter telescopes. The Large Binocular Telescope in southern Arizona, and the WIN telescope, which is listed here as the NN Explorer telescope, which is on Kitt Peak, a telescope I worked at for many, many years and built a lot of instruments for. So it's nice to see that sort of back in action as an exoplanet telescope. So this is kind of the lay of the land of where we are. We're roughly halfway through this sort of listing of telescopes. And from the beginning of thinking about Hubble, which was in around 1976, to the end of the Kepler and K2 mission, which will be about 2018, you see it's taken a number of years, 40 or 50 years, to do that first sort of half of this big plan. So you can imagine it's going to be something like that for the second half of this big plan. So let me remind you where the Kepler field of view was. You guys clearly know the sky very well. In fact, you probably know the sky more than 80% of professional astronomers. So the Kepler field of view was toward the constellation of Cygnus and included a little bit of Lara. That's kind of in the inset on the lower left. And the kind of drawing up here, the cartoon, shows that the search space extended to about 3,000 light years in distance and kind of looked at this one beam in the plane of the Milky Way. So 3,000 light years, if you're traveling that in a spacecraft, is a long, long way, as you know. But 3,000 light years in the big scheme of things is like nothing, right? So it was a fairly local survey of a fairly local part of our galaxy. And of course, anything along that beam there, along that wedge, could fall into the Kepler field of view. And things farther away than 3,000 light years would also be imaged as fainter objects. So it didn't just go out there and stop. There's not a wall built 3,000 light years away. So when Kepler had reaction wheel problems, and some people thought the mission was over, and myself and some clever engineers thought of a new way to operate the telescope using the light from the sun shining on the solar panels to actually act like a reaction wheel, and then using our two good reaction wheels to balance that, we developed what was called the K2 mission. And for your edification and to win money at star parties from other astronomers, I will tell you a secret about the name K2. K2 does not stand for Kepler-2. K2 does not stand for two reaction wheel Kepler. The K2 mission was named after the mountain peak K2. Wow. And I know that because I named it, and I named it specifically after that, albeit with a clever ability for it to be Kepler-2. I named it because, the K2 peak is thought to be just slightly less than Mount Everest. Yet, we all know that the K2 peak is one of the most sought-after climbing peaks in the world because it's a challenge, because it's difficult, and because it's not known as well as Everest. So that's the reason it's called K2. So keep that in mind, go to star parties, bet people, and you'll win some money. So K2, because of the way it works now, has to observe in the ecliptic or in the zodiac part of the galaxy, part of the sky. And that's actually a very nice thing because we see different parts of the galaxy than we did with Kepler. So we can do lots of tests of our planets in the Kepler field of view, the same as planets in the rest of the galaxy. And as you see from this drawing here, and of course you know this because you're all very good astronomers, the ecliptic has parts of the sky where it passes through the Milky Way. So there's young stars, dense stellar regions, star clusters. And it has parts where it looks out of the galaxy, where you can see extragalactic objects and objects like supernovae. So the science breadth of the K2 mission extended greatly over that of Kepler. The big difference was that Kepler stared at a field of view for 4 years. So that means if I was looking for an Earth orbiting a star like the Sun, I would detect a transit of that planet once a year, and over the entire lifetime of the Kepler mission, I would detect 4 transits, maybe 3 if I'm unlucky. So it's a challenging problem to find Earths in the Kepler data. No matter how good Kepler was, you don't have many transits, so you don't get a lot of signal noise by adding them up. The K2 mission is even less of a staring mission. It can only look at any given field for about 3 months. And then it has to turn the telescope and point at a slightly different part of the zodiac. Otherwise, it would end up pointing directly at the sun. And we don't want it to do that. That's very bad. And so it looks at different fields around the ecliptic, but only for about 3 months each. So the two are very complementary surveys in what they've discovered. I wanted to show you this slide. You've probably seen it before. This is the only instrument that the Kepler spacecraft has. It's a large imaging camera. In the top right, you see this person with a bunny suit on when we were assembling the camera. The little blue glassy looking things are charge coupled devices, or CCDs. There are 42 of them in these pairs of 2. Each of these CCDs was about $100,000 in cost. They were specially made for the Kepler mission by a company in Canada, designed by a number of people at Ball Aerospace and myself and a few other engineers to allow us to have very large well depths. So if you know about CCDs, you know that pixels can collect light and they can collect so many photons. And we knew Kepler was going to be looking at very bright stars, and we knew we wanted to collect lots and lots of light, because the more photons you collect, the bigger your signal is compared to any noise that you have. So these particular CCDs, each pixel can hold about 180,000 electrons in a certain imaging mode. They were typically used where you set the voltages differently so that each pixel could hold about 1 million electrons. So that's a number that you won't find in a ground-based telescope, and you don't need it in a ground-based telescope for other reasons. So this is the largest focal plane that's ever been flown in the sky. It still holds that record. It won't be beaten by a larger focal plane until the WFIRST telescope gets launched sometime around 2024 or something like that. Right now, I think I have a little note here. Yeah, that 3 modules have died. Can you guys see my cursor on the screen?
No. We're not looking at your screen.
Oh, that's true, you're not. Okay. 3 modules near the top left edge have died over time, about 1 every 2 years. So the K2 mission only has about another 1.5 years to go, so it's fine. We aren't going to lose most of the focal plane before the mission does. All right, next slide, please. So this is a kind of a stock slide that you use if you're talking about what kinds of science you do with Kepler and K2. And since we broadened the kinds of science, we wanted to try to sell this to the community and to NASA headquarters as a mission that is very focused on exoplanets, but also does a lot of other science. And I want to highlight some of these science goals as I go through the talk tonight. So of course we're going to talk about exoplanets. That's the bread and butter. That was the primary mission of Kepler, and certainly one of the primary goals of the K2 mission. But we're also going to talk about star clusters. We're going to talk about supernovae. We're going to talk about protoplanetary disks in star-forming regions, and I don't have a picture on here, but I'll show you one in the next slide. We're going to talk about objects in our own solar system. So we go to the next slide, which has this is slide number 7. It's a trans-Neptunian object, and these are sometimes called TNOs. And if you followed the whole drama about Pluto being a planet, being a dwarf planet, being a Plutina, being in the Kuiper Belt, being a trans-Neptunian object, various names of things, these are objects that are generally small, they're rocky, they typically don't have an atmosphere, although Pluto and Charon are exceptions to that. And they typically are objects that lie in our solar system farther away than the planet Neptune, hence the clever name of trans-Neptunian object. So the way we observe these with the K2 mission, remember we're looking in the ecliptic. So if you look in the ecliptic plane, which is the plane of the solar system, it's hard to avoid not seeing lots and lots and lots of small rocks flying through your field of view. You don't have much choice, so you can say, I hate them, and I don't want to observe them, or you can embrace them as a great science goal, which we did, and you can observe them in this very interesting way. So this kind of arc-shaped or parabola-shaped path here is a path of pixels on one of those imaging detectors that were laid out along the orbit of this particular trans-Neptunian object during a 80-day observing period when we stared in this part of the ecliptic. So if I was observing a star during all that time, the star would be contained in just one small little set of pixels, much like the dots on this trail. But because this object is relatively close to our spacecraft compared to stars, this is just outside the planet Neptune, and our spacecraft is roughly in the orbit of the Earth, that object suffers parallax during the observation. So we see the objects in the solar system make these parabolic-shaped paths. So we lay out a set of pixels, and then during the entire time period, the object moves along this set of pixels. And if you look at the inserts here, and you see the little red tick mark there, it shows you a particular part of this path, and the little red tick mark shows you this object moving in 3 successive frames, which, if you can see the times there, are about 20 hours apart.
Since you're able to use parallax on that, can you get a direct distance, or can you deconvolve that from the motion of it itself?
We can indeed, because we know where the spaceship craft is, and we can use the parallax here to measure both the object's photometry and its distance. Yeah, it's pretty cool. So we do that. And of course, this object nobody had observed before other than its discovery observation. And it's important to understand the bulk densities of these objects, what they're made of, and their rotation period. So if you look at the next slide, here are 2 examples of rotation periods measured in this way using the K2 mission. The one on the right is, which one is it? JJ43. So JJ43 is on the left, the one we just saw the path for, and on the right is this thing GV31. And these light curves would essentially be impossible to measure from a ground-based telescope for 2 reasons. One is these objects are very faint. You can see their magnitudes there, 20 and 23. So yeah, you can do that with a big telescope if you work hard. But look at the orbital periods of these things, 12 hours and 29 hours. That's a pretty tough period to measure with a ground-based telescope unless you get lots and lots and lots of nights, and in this case on a very big telescope. So far there's been about 500 of these objects measured, and the distribution of the rotation rates through theoretical modeling tells you things about the age of the solar system and tells you things about the formation of the Oort cloud. So this has been a real interesting boon and a real different thing from exoplanets compared to things in our own planetary system. It's been really fun. So in the next slide, it says Neptune movie. I want to show you a Neptune movie. So this is now a movie of us looking at the planet Neptune and its moons, Triton and Nereid. And there's a lot of interesting things in this movie, so let's start the movie if you haven't already. You first might notice a jump in the stars. That's when we're making adjustments to the pointing of the telescope. There comes Neptune, probably already started on yours. You can see Triton orbiting very close to Neptune. You can see Nereid following behind it as a little faint blob. And of course, you see many other solar system bodies flying through the frame at various angles and speeds, because we're looking in the plane of the solar system, and there's a lot of stuff there. The weird sort of pixels in the middle of that are where saturation happens, because Neptune is very bright. But you can collect all the light and still do great photometry on something as bright as Neptune, as well as its moons. And if you notice here, if you run the movie again, if you notice the stars don't seem to move, because we're pointing at stars that are very far away. But again, we have this parallax effect with Neptune, where it comes in, reaches its stationary point, and goes back out of this collection of pixels that we saved here. So it's just a really fascinating movie. This, of course, is not how we did the science. We actually made photometric measurements from these data. But it's a great PR thing, and it also shows that the great value of these kinds of observations. So that's pretty cool. All right, so let's leave the solar system, and in the next slide, number 10, let's move on to star clusters and see some interesting things we maybe learned about star clusters. So here it shows the star clusters on the left, the Pleiades and Hyades, very famous star clusters. You probably know them well. And on the right is the upper Scorpius region, a region in cleverly the Scorpius constellation where stars are forming. These are some of the youngest stars we know in the night sky. And these little squares on here represent the CCD modules that I showed you in that image earlier of the instrument on Kepler. And this shows you the size of the patch of the sky that we observe at any given time. If you also notice here, you see there are two missing modules. When this slide was made, there were only two modules that were dead, and so we didn't include them here because we could collect no data in those two rectangles. And it turns out the third one that died completes the tic-tac-toe line of the triad going across there, and it's on the other edge of the focal plane. So this gives you an idea of how large a field of view we look at any time. Sorry, was there a question?
No, we were just debating which one you meant by.
I meant the one that's on the opposite side of the Pleiades in the middle.
Oh, there, okay.
So if you take those three, that's the third. So here's a kind of a fun result that was done by a graduate student that worked with me for a summer. So one of the things that people know about stars is that stars rotate very fast when they're first born and when they're very young. And as stars get older, they slow down. They slow down because they lose angular momentum, because they have magnetic fields and they have solar winds. And those winds take angular momentum away with them and the star slows down. So you can make a diagram that tells you things about ages of rotation period, and that's what we have here on the the vertical axis, period in days, from 0.1 days at the bottom to something like 15 days at the top. And you can plot that as a function of mass of the star, and that's on the bottom axis here, the horizontal axis. And on this scale, 1 is 1 times the mass of the sun. So small stars evolve slower than more massive stars. So therefore, you would expect that stars that are the mass of the sun or more massive here would have slowed down because they're older. And stars that are smaller mass might still be spinning very rapidly. The gray points on here were what was known about the Hyades cluster rotation before we made an observation. And if you ignore the red points for a minute, you can see that those gray points have a very nice relationship. You can imagine drawing a line through those points. And you can imagine saying that stars that have a mass of 0.2 times the mass of the sun should have a rotation period of 12 or 14 days. Seems quite obvious from that relationship. However, that's because nobody really spent a lot of time looking at the very low mass stars in the Hyades until we did. And you can see those red points, which are added points from our observations, show that somewhere around 0.3 solar masses, the relationship changes dramatically. And this is a place in models and a place that astronomers believe happens at the insides of stars, that the stars become a fully convective body at that point. That means that from the center of the star all the way to the surface of the star and back to the center, They have these large convective cells that move material the entire way through the star. The sun, however, and stars that are more massive than about 0.35 times the mass of the sun, they're only convective in the top half of the star. They have radiative cores. So if you could ride in the sun's convection cell, you would only dip into the sun about halfway down in its radius, and then you'd be buoyed back up to the surface. But if you did that in one of these very small stars, you'd ride all the way into the center and back up to the surface. Of course, you'd be dead in both those cases, but it would be fun. All right, so that's a pretty neat result there, and that, of course, changed what we think about low-mass stars. Going on to a really young star-forming region, so these are stars that are between 1 million and 5 million years old, so an M, not a B. These are very, very young stars. In fact, they're so young, they still have disks of material around them that are forming from the cloud that formed the star, and probably in those disks of material, planets are forming as we're observing them. So on the left side, you see a picture. This is a picture from Spitzer of this Rho Ophiuchus star-forming region. And the dark things there are very dense regions of molecular gas. The lighter part are very undense regions, but still of gas. And all the dots on here are stars that were observed, and some of their light curves are shown over here on the right-hand side. The blue points represent all the stars that were observed. The red points represent stars that were observed that are now known to be binaries. And you can see that there's a fair number of binaries. It's not a very unusual thing to be a binary star. And the interpretation of these light curves on the right-hand side, which are called now bursters, and you can see maybe why, because they go along and they eventually burst with a brightening. This is thought to be large chunks of the circumstellar disk that's falling onto the star. And as it falls onto the star, it heats up a large chunk of the star's atmosphere, and that increases the light output from that part of the star by raising its temperature tremendously. And you can go through each of these bursting things, and you can kind of see in some of them, you might believe they're periodic. The one on top has a section that looks periodic here and there, and maybe the one on the bottom, you can't see anything that looks periodic. So there's a lot of study here to try to match theory to observation, and so far people are well behind in theory compared to these observations. And now one of our favorite star clusters, we can look at the Pleiades. The Pleiades, as you know, is the 7 sisters, and I think it's actually 6 sisters and their mother, if I remember right. I think Pleione was the Greek mother of the other ones, but anyway, we call it the 7 sisters. And the 7 sisters are an interesting asterism. The Pleiades, the word comes from some Latin word, I think it means to sail or sailing, because it was clearly one of the greatest navigational aids in the night sky for sailing in the Mediterranean. You can find it all the time, it's pretty obvious. And here we see each of these little boxes that points to one of the bright 7 stars is a light curve of that star. And this really has baffled astronomers, and we still don't know the answer here, because each of these stars, each of these bright stars, is roughly the same mass. This cluster all formed at the same time. It all formed from the same gas, the same metal content of the gas. The stars are all the same age. Wouldn't you think they'd all have the same kind of photometric pulsations and photometric variability? And they don't. The one that's really different is the one on the right middle, which is Maya itself, which is now known not to be a Maya variable. So it's the name of a class of which it no longer belongs to. It's kind of funny. And you can see the very clear variation there. It looks like a sine curve. And that variation is about 10 days. And from using this light curve and spectroscopy of this star at the same time, it's known that variation is caused by a large spot of odd chemicals that exist on one side of the star, but not the other side of the star. And no one knows why, no one has an explanation. So very, very fun thing for astronomers. And here's stars that we always thought are perfectly identical. They're just great. We'll know everything about them as soon as we understand one of them.
So
and you can see that we don't understand any of them.
So is that another alien megastructure?
Absolutely. I think one of you should write a paper on that. Yeah, let me tell you another interesting thing we found with stars. So this is a a diagram. This is not a real observation here. It actually is pictures of the sun. I just made them bigger to illustrate the point, and I used different wavelengths so you wouldn't think they're all the sun. So they show the relative size of the sun compared to some stars that we call giants, which are in the middle here, and other stars which we call giants or large giants, which are on the right-hand side here. So this again is no real shock. You guys probably know this, that not all stars are the same size, and the sun compared to giants is not that big of a deal. It's sort of an average star. But there were a class of giants that were found in the Kepler field that look like this. And again, this is an illustration. We don't have pictures like this of these stars, but we did observe these stars. And this is a diagram that was made to try to illustrate the point of what we found. So it shows in relative size the sun versus one of these giants we discovered, which has this clever name of KSW 71. And this object rotates in only 4 days, I think, or 5 days, even though it's this much larger than the sun. So it's rotating very fast. That's why it's drawn here as being sort of mushed down or prolate, because it rotates so fast the equator bulges out. And this star and many of the stars that were found, we now know about 40 of these in the Kepler field, are rotating nearly at a fast enough speed that they would fly apart or break up. They're rotating at roughly 80 to 90% of the breakup speed. And this is a problem because you can't make a star do that. We don't know how to make a star do that, a single star do that, especially if it's a giant, because when you go from a star like the sun, the star evolves and becomes a giant, it gets bigger, it expands. And if you've been on ice skates or watched an ice skater, you know that as you move your arms out, you slow down, you don't speed up. So these objects, typically giants, rotate at instead of the sun rotating at about 25 days, giants typically rotate at hundreds of days. But we found this class of objects that rotate in just a few days. And the best explanation for these is that this object is actually not a single star. This object is actually a very close binary that has recently merged. The two stars have merged together. And when I say recently, I mean, of course, something like in the last 10 million years, maybe. But they've recently merged, and now they look like one star on the outside. But if you could look at the inside of the star, there would be two cores rotating around in there. And that merger takes the angular momentum of the binary system and gives it to the angular momentum of the rotation and spins these stars back up to tremendous speeds. So pretty fun discovery based on looking at Kepler light curves and trying to understand why some stars look weird.
Question.
Yes?
If it was a merger of two stars and the cores still survive in there, it wouldn't be a spheroid, would it? It would be more bilobal, wouldn't it?
Well, the cores are relatively small and they're relatively near the center.
Oh, okay.
And so you just don't notice them.
Okay.
And we have no real way of observing into a star. So again, this is speculation where they came from. Now it does turn out that roughly the number of these that were found so far in the Kepler field is in agreement roughly with the number of these very close types of binaries called W Ursa Majoris binaries. So at least the space density, the number that could make them, seems to be roughly consistent. So it's pretty cool. So stars are not as boring as we thought. They're not just spheres that sit there and do nothing. So now we're going to move kind of far away from stars. We're going to go to cosmology. This is slide 16. And we're going to talk about dark energy a little bit. We're going to talk about standard candles. I'm sure you all know, have heard of the type 1a supernovae, and you measure the distance of these objects, and it tells you something about the early universe, and you can use those to go back in time, and astronomers have found this place in the universe where material seems to have accelerated at a different rate than it does now, and they've advocated a mysterious force called dark energy that did something during this one time of the universe. And so observations of supernovae are quite important because you can see them at faraway distances. I show an example here of a supernova in the bottom right corner. This is a beautiful picture of a galaxy, and that white dot there down in the corner is a star that belongs to that galaxy, but it's just blown up into a supernova. And you can observe that star across the universe. Supernova can sometimes become brighter than the entire galaxy for a brief period of time. So understanding those is very important. However, one thing that we've never seen before in observations of supernova, but models have predicted them, is what happens in the very first few hours of a supernova explosion. So let's see if we can learn anything from that particular time period. So here is an example in the top left. I'm sorry, I'm on slide 17. I moved to the next slide without telling you. The top left shows two supernovae that were observed. The one on the left says something about the stellar radius there, and the one on the right has a stellar radius also. And they both are thought to be red giants like Betelgeuse that blew up, their cores collapsed, and they became supernovae. And these are called type 2 supernovae, and they're fairly well understood in that it's a single star whose core runs out of fuel, it collapses and blows the star apart. So you can see a couple things. You can see that the very left one up here, the one that's 2011A, the green line is a model fit, and the red dots are the real data, and you can see it doesn't fit very well. So we don't understand what happened here. We can't predict how this particular supernova should have worked. The one on the right looks like it really fits well, and you think, wow, okay, we got one right, that's great. But if you look at the inset, that little part on the bottom there that's zoomed in to the lower right there, the red dots are the data, the green line is a model, and the light green line is a fit to the data. And you can see there's that spike that happens there around the time 0, which is the time when it's thought the actual explosion started. And that bump there has never been observed before for two reasons. One is you can see it's not very big. And two is, if you look at the full supernova light curves back on the left-hand side here, when the star explodes in the first few hours, it's still fairly faint. It takes the star many days to reach its peak brightness. And roughly when it gets to its peak brightness is when some observer on the Earth says, hey, there's a supernova in that galaxy. And until then, it's generally too faint to be seen. So what we did with the K2 mission is we stared at thousands and thousands of galaxies, hoping, just hoping, that during the time we were looking, a supernova would happen. And then once we knew that a supernova happened, we can go and look at the data on that galaxy and find the data before the supernova happened, and then see the brightening of that supernova in the first few hours. And you detect things like are shown here. You detect that you don't understand model fits, and you also detect this bump on the right-hand side. And this bump has been predicted theoretically since around the 1940s, but nobody had a chance to ever observe it until now. It's only been seen once, and this is the observation right here, and it's called the shock breakout. And this bump represents light radiation from the center of the star that goes through the star and breaks through the material surface of the star before the material surface of the star starts exploding outward. And that's because light travels faster than the explosion of the material in the star. And when that shock wave of light breaks out through the surface, you see it here as a brightening, a shock. And then the material from the star follows it. So it's pretty cool. And you can do all sorts of modeling of that and tell everything about how the interior of the star blew up. And we hope to see that in many, many more. We now have observed about 25 supernovae, which are all in the state of being modeled in such a thing. So that's one interesting thing. And these are type 2 supernovae. These are stars that are single stars. But what about the standard candles? What about the things that tell us about cosmology? So slide 18, the next slide, shows an observation of a type 1A supernova. So type 1As are the standard candles. These are the things that people observe all over the universe, and they put them on plots, and they tell you what the Hubble constant is, and they tell you about dark energy. But nobody knows what causes a type 1a supernova. There are theories, but there are no absolute facts or observations that tell you what the thing is that blows up in a type 1a supernova. So here's the first supernova that's ever been modeled in the first few hours that will tell you exactly what blew up. And again, we have about 20 more of these, and eventually we'll be able to tell you what the progenitors were to 20 supernovae of type 1a. They might all be the same object. They might be 20 different objects. We don't know yet. But either way, it's going to make a big statement about standard candles or not. In this particular case, the red line on the main plot here is the supernova light curve. People on the ground would start observing this around day 10. So the first 10 days of this would be missed by people on the ground. The little arrow there at 0 points to the time that the explosion happened. And if you look at the inset, the little blow-up part up there, you see those various colored lines that show you model fits from theory of what this light curve would look like if different kinds of things blew up. And the only line that this model is consistent with is that bottom blue line that barely is above the data. And even that's a little too big. It goes above the data. So in this particular case, the models would suggest that this supernova was caused by two white dwarfs that merged together, went over top what's called the Chandra-Sekhar limit, and blew up. So this particular object is pretty well now known that it was two white dwarfs that merged together. The question is, are other standard candles going to be two white dwarfs that merge together or not? Time will tell. We have many more of these to look through. All right, let's go to slide 19. So we're going to talk about exoplanets a little bit here. I like looking at history and looking at quotes. This person here, Lardner, was a very famous writer of popular science books in the late 1800s. And he was such a popular writer that almost every house that had anything about astronomy or philosophy would have one of his books in there. And so the population, the general public, knew astronomy from his books. And his books for a number of years led many people in the public, and even many astronomers, to believe that planets could not be detected orbiting other stars. He talks here about maybe these variable stars we see are due to planets passing in front of them, and then says, but this is just conjecture, it's a hypothesis, it can't really work. And so this was a person that made big statements and actually caused a lot of other speculation, a lot of serious astronomy to not go very far, because people said, well, this guy, this famous guy writing astronomy books, said that it can't happen. So, we always got to be aware of what we read. So let's look at slide 20. This is a slide you've probably seen before. It shows all of the planets that have been discovered by Kepler and the planet candidates here. Most of these are now known to be true planets. You see orbital period on the y-axis from 1 day out to about 1,000 days. And on the y-axis is the size of the planet relative to the Earth being a size of 1. Neptune's about 4 times the size of the Earth, and Jupiter's about 10 times the size of the Earth. The yellow points here are just the most recent planets found. There's nothing different about them. It's just that it shows that the most recent planets found, the ones that are new discoveries, have longer orbital periods. And this makes sense because, as we talked about earlier, if you have a long orbital period, you don't make many revolutions during the entire 4-year time that Kepler looked. And therefore, it might take 3 years to get enough signal noise to discover that that planet exists. So that's all this is showing you, that planets are everywhere, and small planets are pretty popular, much more popular than large planets. In slide 21, I just wanted to show you one kind of interesting multiple system that's recently been discovered. The top of this plot shows our solar system. Mercury, Venus, Earth, Mars, and then Jupiter, Saturn, Uranus, and Neptune, and Pluto way over there on the right. Once again, we put Pluto in because I made this plot, and I'm putting in Pluto. So you can see that the planets there, obviously the sizes are to scale here, and they overlap. But you see Mercury on this scale starts at some distance from the Sun, and a semi-major axis that has an orbital period in our solar system of about 88 days. And Kepler has found many solar systems that have planets much closer to their star. They're packed in much closer. And this was, initially an interesting discovery because we thought every solar system would look like ours, and of course they don't. We just don't have a lot of planets close in, but it seems pretty common in Kepler data. But the system I wanted to point out here is down there at the bottom, Kepler 444. This system is an interesting system. It has 5 very small planets. You can see they're all Earth size or even smaller. They're packed together very close in distance from their star. And this particular object is the oldest planetary system known. In fact, it's one of the oldest stars known. It's a star that resides in the halo of our galaxy. And we were just lucky enough that during the 4 years that Kepler stared at the field of view toward the constellation Cygnus, this halo object that orbits our galaxy in the halo was passing through the plane of the galaxy while we were looking there, and happened to be a star in the Kepler field of view, and happened to have its solar system turned directly in our direction so we could see the transits of these 5 planets. So that's pretty cool. So it's the oldest solar system known. These planets are all small and rocky planets because they're smaller than the size of the Earth. We of course don't know anything about the possibility of them having life or not. They're all so close to their star that they would be very hot, and there could be planets further out from this star, but it's very difficult for Kepler to find planets with periods longer than about a year, even though it looked for 4 years. So solar systems with planets farther away than about a year are still things that we don't have much information on, because Kepler is the biggest planet-finding mission, and it just couldn't do it. If it had stared at that field of view for 10 years, we might know about planets with orbital periods of 6 years or 8 years. And again, how long can you stare at a thing? So in the next slide, number 22, just shows you the current planets that are roughly the size of the Earth that we believe exist in the habitable zones of their stars. And these are Kepler discoveries. There are many more discoveries now by the K2 mission, and I will end the talk tonight with one of the coolest discoveries that's been made in recent times in exoplanets. So you can see here there's a number of objects that could possibly be places that have life. Now I mentioned that Kepler can't find planets very far away from its star, and that's because it has to look for a long, long time in order to do that. But in the next slide, number 23, there is a technique that allows you to find planets that are massive, like Jupiter and Saturn, and allows you to find planets that are far away from their star in orbits of 20, 40, 80, 100 years away. And this is a technique called microlensing. And this has been done from the ground for many years. It's now being done by spacecraft like K2 and Spitzer. And you observe a star, and if you see on the right-hand side there's a faint object in a green circle. If you play the little movie, I think there's a movie here. Is your movie playing?
Yes.
Okay, you'll see the red dot on the bottom, which is the light curve, but you also, if you look up there at that little green circle, you'll see that star gets incredibly bright for a few moments. And there are 2 spikes in the light curve. It's kind of hard to see those with your eye in the top movie. But those 2 spikes represent planets that pass in front of that star and cause the light from that star to be gravitationally lensed for a brief amount of time, and therefore the star looks brighter. And by measuring those spikes and the details of that light curve, you can tell something about the mass and the orbital periods of those planets. So this technique is very complementary to Kepler in that it allows you to find planets that are far away from its star, and Kepler allows you to find planets that are close to your star. Let's skip slide 24. We'll talk about it in slide 25, though. So slide 25 illustrates how you can possibly measure the atmosphere of a planet. And it's a simple technique in principle. It's very hard in practice. So you observe a star, and when the planet passes in front of that star, so the planet is transiting, some of that starlight passes through the planet's atmosphere. A very little bit of it passes through the planet's atmosphere. And if you can measure the star when the planet is not in front of it, and you can measure the starlight when the planet is in front of it, the difference in those measurements tells you something about the atmosphere of that planet. So this has been done successfully with ground-based telescopes, the largest ground-based telescopes, for a very few planets that are large, like the size of Jupiter or Saturn. But what we want to do with this is we want to do this for planets that are small like the Earth, because we want to see if their atmospheres have things like our atmosphere has. First, we'd like to see if they even have an atmosphere. And then we'd like to detect things in their atmosphere like water vapor or chlorophyll or pollution, something like that. So if you look at the next slide, it looks kind of technical and crazy, but it's pretty easy to interpret. Each of these bubbles is a planet, and each of the bubbles represents a sort of a mathematical probability that JWST, the James Webb Space Telescope, will be able to observe the atmosphere of that planet. The smaller the bubble, the better the chance the atmosphere can be observed. So you can see the small bubbles fall to the bottom of this plot and slightly to the left. The blue chunk here is the habitable zone. That's where planets reside that would have kind of the right conditions that could be like the Earth. So if you have a small circle in the blue thing, that's a good candidate for JWST to measure its atmosphere. The brown circles, or whatever that color is, those are planets that were discovered by Kepler. The blue circles are planets that were discovered by the K2 mission. And you can see the blue circles are really filling in an area that's going to be an exciting place to look with JWST and possibly measure the atmospheres of some pretty small planets and hopefully find things that are like the Earth. So that's pretty cool.
Very cool.
So I want to move away from planets per se for just a minute and look at slide 27. This is a slide that shows 4 possible ways that you might observe a planet transit, or you might observe something that looks like a planet transit but really isn't. So the top left shows you a planet transit. That's a real planet. It's orbiting around its star. The other 3 cases show you things that look like planet transits, but none of them are planet transits. The one, number B there, is a small star that goes in front of a big star. D at the bottom are just 2 stars that orbit each other. And C, the bottom left, is a star or a planet that orbits a star or a planet that's actually not the star or planet you think you're orbiting, but a fainter background star. So the question is, if I see a planet transit, what do I do to prove that it's case A here compared to those other cases, which we would call false positives? And the reason that's important is in slide 28. So slide 28 tells me that I have a planet on the left that's the Earth. I know the Earth has a radius of 1 Earth radius. The planet on the right is Neptune. That planet has a radius of about 4 times the radius of the Earth. I know the Earth has a solid surface with some liquid water. I know that Uranus or Neptune are big gas giants. They don't have solid surfaces. They don't have liquid water on their surface. And then I show here just a sample of Kepler planets, which, as you can see, are bigger than the Earth but smaller than Neptune. And we don't know, in these planets, are they gaseous, are they rocky, are they ocean worlds? We don't know the average density of these planets, and we don't know which ones might have atmospheres. So we would like to not only prove what things are really planets, we would also like to prove what things have the right size, the actual size, to be something that can possibly be rocky. So in the interest of time, which you will lose no information whatsoever, let's skip to slide 30, because it's pretty. Slide 30 is a view of Mauna Kea from an airplane that was flying over Mauna Kea. And this shows you all the telescopes up on Mauna Kea, including Keck and the Gemini telescope on the right. It also shows you the island of Maui in the distance with Haleakala, which has some telescopes on top of it as well, including, as you guys probably know, the site of the largest solar telescope in the world.
La 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 la.
We know it will not be nearly as good as Big Bear. All right, so the next slide, number 31, shows you the Gemini telescope up close, and if you click, it'll show you the Gemini telescope even closer on the inside of that. And on the right-hand side, you see a weird little white metal structure-looking thing with a tiny little silver box in the middle. This is the smallest instrument that Gemini has ever put on the Gemini telescope. It's about the size of a carry-on suitcase and it weighs about 40 pounds. And this is a very cool instrument called a speckle interferometer. And what it does, well, let's go to the next slide. I'll show you what it does because it's easier to show you than describe it. The next one just shows you the layout of it. The light comes in and it splits in with a beam splitter to two separate cameras, so we observe in a red channel and a blue channel simultaneously. And if we go to slide 33, this shows you an image of a binary star. The entire field of view here, this black square, is 1 arc second across. So it's kind of a great scale here. And this shows you, as you step through clicking, this shows you 4 sample images taken by our camera, each of them lasting for 50 milliseconds. So you take images like this, and the images look like little blurred speckles, and that's why it's called a speckle interferometer. And the way it works is you gather thousands and thousands and thousands of images like this, each of which is taken so fast that it freezes the atmosphere above it. And by combining all those images with mathematical Fourier techniques, you can remove the complications of the atmosphere and therefore reconstruct the image you would have seen if the atmosphere was completely gone. Now, some of you may know what's called adaptive optics, or AO, and that's a similar kind of technique, but uses typically a mirror or some surface that modulates very quickly and in real time corrects for the atmosphere and gives you an image that's now a summation of a bunch of corrected images in real time. We don't correct any of our images in real time. We correct them mathematically in Fourier space and then add them back together. Pretty cool. So let's go to slide 34.
By the way, here at BBSO, we both, of course, have a rather nice AO system, but we also do speckle reconstruction and post-processing.
Excellent. You guys know all about this then. So if you play the movie of this slide, slide 34, you'll see a speckle images we take on the left-hand side. The integrated image means if I was just looking with a CCD for 5 minutes and I just took an image. And on the right, you'll see what the reconstructed image turns out to be after each of these sets of speckles are processed in Fourier space. So you should end up seeing on the right this really cool, well-separated, high-resolution binary. And again, each of these boxes is 1 arc second on a side.
Very nice.
So the next few slides are just stepping through examples. Slide number 35 shows you the reconstructed image of a point source. Hey, it looks like a point source. That's great. Slide number 36 shows you the reconstructed image of a binary that's separated by 1/3 of an arc second. And you can see that the images, when you add up all those speckles in Fourier space, you get a fringe pattern. And that fringe pattern allows you to know what object or objects made that fringe pattern. It tells you their relative brightnesses, it tells you their separation, and it tells you their position angle or the orientation they are on the sky. And you can see that between this slide and the next slide. If you stare at this slide, you'll see that the fringes go from the lower left to the upper right, and that means the binary goes from the lower right to the upper left. And notice the spacing of the fringes here, and notice the spacing of the binary. If you click to the next slide, which is 37, you can see pretty much the opposite. The fringes go the opposite way, their fringes are closer together, therefore the binary is the opposite way, and the stars are farther apart. So it's a pretty simple idea, and it works pretty well. Slide 38 just shows you some examples of different fringe patterns. It's pretty uninteresting. But in slide 39, I wanted to show you a cool thing we did as a test when we had our camera on the Gemini telescope. This is a reconstructed image of the asteroid Cleopatra, and you can clearly see here that the asteroid Cleopatra is like a dog bone in shape. The two images here are from our red camera and our blue camera, and one of them, because we have a beam splitter, one of them is a flipped image of the other. That's why they look like they're in opposite directions. But this is the first true image of this asteroid Cleopatra. So now we have a program we're collaborating with people that are trying to image many, many asteroids with our camera, so they can look and see if they have satellites, or if they're spherical, or if they have shapes like dog bones, and learn a lot more about the asteroid belt. The next slide, number 40, shows what used to be the highest resolution image of Pluto and Charon ever taken. This was taken in 2012, and the top image is Pluto, the bottom image is Charon. You can see the scale bar there of 1 arc second. And this image had a surface resolution on Pluto of 400 kilometers. And in fact, in the original data, we went back and looked at it after New Horizons flew past Pluto. And in this image, which we kind of noted at the time in our notes in our science notebook, but we didn't put into the paper because it was about a 1 sigma detection, you could detect the bright heart-shaped region on the surface of Pluto. So we could have been heroes, but we didn't. We just didn't have the signal noise to believe it. The next slide just shows you an example of a panchromatic image. That is just a long integration with a binary, and then just another way of showing it with a plot. And by doing this work with Kepler objects, we've looked at about 900 Kepler stars that host planets. We've determined that about half of those are binary stars. So we've all learned in Astronomy 101 that half the stars are binaries. Well, it turns out that roughly half the stars that have planets are binaries. And that's a real problem. And it's a problem because in this particular case, I don't know which star the planet orbits. Remember, Kepler had 4 arc-second pixels. Here you see a 1 arc-second scale bar. But even if Kepler had 1 arc-second pixels, it would not have the resolution to ever separate these two objects. In fact, basically no telescope can separate these two objects. Even Hubble, we can do far better than the resolution of Hubble. So if I don't know which star the planet orbits, I don't know the size of the planet. Because the transit technique gives me the size of the planet only if I know the size of the star it orbits. It's a ratio of the area of the planet to the area of the star. So in this case, if the planet orbits the star on the right, which is brighter, the planet will have a certain size. If it orbits the star on the left that's fainter, the planet might be a larger planet. And in fact, in some cases, if the binary has such a difference in brightness ratio, if it orbits the fainter star, it might not be a planet at all, but a star. So this has really complicated us knowing the sizes of planets. And since half the stars are binaries, half the planets might have the wrong radius. So it's a pretty interesting complication. We worry about whether these stars we see are true companions or not, because we want to look at the how many binaries there are, how many true binaries there are. And this is just a plot. If you know anything about isochrones, these are the gray lines on here are models, and isochrone means the same time. So all of these models in a diagram of some color on the horizontal axis versus a magnitude on the x-axis, you can fit models to this. They're all the same age, because if it's a true binary, we assume the stars formed together. And you can put the dot on here for each of the 2 stars you measure, and if those 2 dots fall in the same isochrone, you believe the 2 are really a companion and orbit each other. If they don't, you might believe that the star you see is just a background line of sight star. So the next plot, number 43 here, shows you how a planet radius might change if it orbits the bright star or the faint star. And the important message here, I think I've already told you. If it orbits the star that we call the primary or the brighter star, the planet radius is probably correct, or correct to about 20%. But if it orbits the faint star, the planet radius might be wrong by factors of 8 or 6 in radius. So if you have a planet that's the size of the Earth, but it really orbits the faint star, it might be 6 times the radius of the Earth, which means it's really more like Neptune. It's not like the Earth at all. So this is a confounding problem that we've created, and now we have to try to figure out what to do about it. So far, I don't know the answer, but we're working on it. All right, and I want to close with a little bit of stuff starting in slide 44 on what I believe is the best exoplanet system we've yet discovered. This is TRAPPIST-1. If you haven't heard about TRAPPIST-1, you've been living under a rock. TRAPPIST-1 is a star in the southern sky. It's a M8 or M9 star, and if you know what that means, it means this star is very cool in temperature. It's about the size of our planet Jupiter. This particular star is only 40 light years away in astronomy. That's like a next door neighbor. And so far we've discovered 7 Earth-sized planets that orbit this star. 3 of them orbit in the habitable zone. Slide number 45 just gives you a cool little comparison between the Sun and our terrestrial planets, TRAPPIST-1 and its family of planets, and the planet Jupiter and its little solar system of the 4 Galilean satellites. Kind of a neat comparison there to show you that this is a tiny little world. These stars orbit, or these planets orbit around TRAPPIST-1 with very short orbit periods, yet 3 of them are in the habitable zone. The star is so cool that you can be very close to it and be in the habitable zone. Slide 46 shows you a template there of where K2 observed. You now can clearly see the 3 dead CCDs. So apparently I lied before. They are not in a diagonal line. There are 2 across the top. The blue line there is the ecliptic, and the inset on the top right is what an image of TRAPPIST-1 looks like with those giant 4 arcsecond pixels in the Kepler focal plane. So they're not pretty, but they do great photometry. Slide 47 shows you the observations that we made of TRAPPIST-1. The red points are the raw data. The blue line is a sort of median fit to the data. There's an area near time 2955 where you see there's no data points. The spacecraft there went into a safe mode. That is, it had a problem that the software couldn't fix. So what it does if it has problems the software can't fix is it puts the spacecraft in a pointing orientation, so it's sure that it's not going to point at the sun, but it makes sure the solar panels are pointed at the sun so you can keep the batteries charged, and it points the antenna toward the Earth and says, help, 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 help. And astronomers then and people that monitor spacecrafts hear this. It really doesn't say help. And we all know no one can hear you scream in space or something like that from the alien. Anyway, and then you fix it, and eventually you go back and observe the object. So you notice a few things here, that the raw data here has a little bumps and wiggles to it, which may or may not be real. That'll have to come out in processing. But the blue lines there show you very clearly a periodic signal, and this is believed to be the rotation rate of TRAPPIST-1, which is approximately 3 days. And these are star spots on the surface of the star orbiting around that we see. The next slide shows you the transits of the 7 planets that have been revealed. This data is about 1 week old. You are probably one of the first 20 people to see these light curves, so that's very exciting. Here are the 7 planets here, the 7 transits around TRAPPIST-1. The middle 3, so if you go 2 down and then forget the bottom one, those middle 3 are the ones that might be habitable. So if you look real closely there, you might see people waving or something like that.
Really?
Yeah, not really. So let me show you what we did with our Great Speckle instrument to prove that these planets are the right size. Remember, if there's a binary companion, the planets might not be the right size. You want to look at stars and make sure the star is a single star. That way you know the planet sizes you measure from the transits are actually the right size. So on the left here is an image of a typical star. It's about 1 arcsecond across. On the right here is an image of a Kepler planet candidate. In this particular case, you can see it has a very faint companion. So if we saw something like this, we would be worried that the planet sizes we measure from the transits aren't quite right. In the next slide, number 50, you can see happily the image of TRAPPIST-1 on the left. It's a single dot. There is no other dot anywhere near that dot. And on the right, we show you the scale of how well we can see and peer into the TRAPPIST-1 system. Shown in the very center is a circle that's the orbit of Mercury, if Mercury orbited TRAPPIST-1. And the outside circle is the orbit of Uranus, if Uranus orbited TRAPPIST-1. It's about 34 AUs across there, and we can see into a resolution of about 0.3 AU. And we know then from this observation there is no other object that orbits TRAPPIST-1 that's any brighter than a Jupiter luminosity planet. So that means that the transits that are measured give us the true sizes of those planets, and the true sizes of those planets mean that they really are Earth-sized and really are very small, as we see in slide 51. where we compare the TRAPPIST-1 7 planets, artist concepts, of course, to Mercury, Venus, Earth, and Mars in our solar system, real pictures. So the artist had to think of 7 different ways to make something look kind of like an Earth. And so this slide shows you the orbital period and various things like that about each of the planets, but you notice they're all very small. This is such a great solar system. They all transit. They're all very close to us in space, 40 light years away. They're all small. 3 of them are in the Howell zone. And all of these planets have a good chance of having their atmospheres measured when JWST gets launched. So this is the greatest planet system I believe we've yet discovered. This was not discovered with Kepler or K2. This was discovered with a very small ground-based telescope in South America. So ground-based telescopes still rule the world.
Yeah.
And the last slide, I just want to summarize and basically say the things I already said. So I will stop there and take any questions you guys might have.
Awesome. Questions?
Hey Sal, can you bring me a charging cord? Sorry, I'm about running out of power.
Yeah, I have a question, but shall I move forward?
I'm not running out of power, my computer is.
We can hear you come in.
Yes.
On the Hyades orbital periods, those were done with star spots?
Those were done with star spot jet thing.
And those
Those were done with rotational curves. So we looked at the Hyades for about 80 days and then measured light curves that kind of looked like the TRAPPIST-1 light curve that had ups and downs, which were spots on the star, and then measured the orbital period from those.
Okay, and that couldn't be done from the ground. We can't. He's disappearing on us, but.
I'm sorry, I've got to plug my computer in. You know, it could be done from the ground, and I showed you some points on that plot that were done from the ground. The 2 differences that couldn't be done from the ground, or would be extremely difficult, were that the lower mass stars, the ones that showed those red points that dropped off to the side, those stars are 18th magnitude and fainter.
Yeah.
So that makes it very challenging from the ground. And they have rotation periods of even though they're short, their rotation periods are a number of days. So to do that kind of work from the ground is very difficult. You need a big telescope and you need weeks and weeks and weeks of time, and that just never happens.
Nobody did it, yeah.
Yeah.
Oh, I have a second question about, you hit so many great topics that I just got a list of questions.
Well, I'm glad. So great, that's good.
The supernova 1A, I thought the traditional picture was that it was a binary star, which one star was pouring material into the other, and it exceeded Chandrasekhar's limit and blew. Is that not the case now?
Well, that was the traditional picture, and if we go back to that slide, let me try to find what it is on mine. That would be slide 18, I think. You can see that on there are a pink line, a green line, and a blue line. And those 3 lines are models of a star that would be dumping material onto another star. And so if that was the case, the data would follow one of those curves. And it doesn't.
Yeah. And so you said you have 20 other cases that you're going to see if the traditional model is wrong.
That's right.
Wow.
Or if it's half and half or something. We don't know yet.
Yeah.
Yeah.
That's amazing.
And I assume on that, if there were 2 white dwarfs that merged, that would not necessarily be going off right at the Chandrasekhar limit. That could be exceeding that by quite a bit. So I guess that's why it's questioning whether you could still assume it's a standard candle.
Yeah, if some of them are a binary star with a star that dumps matter on a white dwarf, and some of them are 2 white dwarfs that merge, then are they really standard candles?
Yeah. Yeah. That's, maybe there's no dark energy then.
Maybe not. I think we're going to make a statement about that, and maybe there is and maybe there isn't, right? Don't know.
Yeah, that's really cool. Another question was this controlling the attitude with a solar panel. Does that achieve the same, pretty much the same pointing as with a gyro or with a traditional system, or is that do you have degraded pointing?
It gives us the same pointing, but not consistently. We have to make adjustments to the pointing to put it back where it was. And if you watch the Neptune movie again, you'll see those jumps that happen. And those jumps in the locations of the stars are when we actually fire pairs of thrusters on different sides of the spacecraft and readjust our pointing back to a perfect place. And then it'll last for about 8 hours or 12 hours at that perfect place. But then eventually we start getting pushed away a little bit by the sunlight, and we have to readjust it with another thruster firing.
Wow, that was really ingenious to save that mission. That was really good work.
Is the thrusters what will ultimately limit the life of Kepler or K2?
Sorry, was the question, what will only limit the light?
You were talking about having to readjust using thrusters. Is it the
Right.
onboard fuel that will ultimately limit the life? I think you said that 2018 was about the end of the mission on that.
That's correct, yeah. Once we run out of fuel, we won't be able to make those adjustments anymore. And eventually that small drift would just keep increasing, and we would just drift completely away from the field of view, and there's nothing we can do about it. And it's hard to know exactly how much fuel you have left. So 2018 is the rough estimate of when we'll run out.
Other questions?
I have a question about the detector material. How do you get, what do you use for the detector material such that you're able to get deep wells like that?
It's silicon, just like in a CCD, but in the wafers that we made were much thicker than typical silicon wafers that CCDs are made out of. And then you have to basically implant material into the silicon. You dope it, if you know that term, to allow the electrons to actually move through wells that large when you apply voltages.
Okay, yeah, no, I worked on the MIPS detector development, so we were using gallium doped germanium in order to get deep wells.
Sure, you had deep wells, and you also wanted to detect infrared photons.
Uh-huh.
Yeah.
And back then everyone said, you can't do it with silicon.
That's right, can't do it with silicon.
We have another question here.
Well, this is more of a general science question here. So the TRAPPIST-1 system is extremely interesting. One thing that strikes me, though, is we talk about habitability zone, and if you have stars that close in, I mean planets that close into their host star, in practice, wouldn't tidal lock and radiation levels be real problems for potential habitability?
Those certainly are things that we think about, and some astronomers are deeply involved in looking at that. There are models that show that if you are tidally locked, you might have a very hot side and a cool side, and maybe the terminator parts would be fine. Or you could have winds if you had a dense enough atmosphere that bring heat around to the back side and make it temperate. Flaring events, especially on M stars, are also a worry, because flaring events can have a lot of high-energy particles in them, and they can have a lot of Lyman alpha photons in them, which are both seriously bad if you have no protection from them. But there are also studies that show that maybe that happens only in the very early life of the star, and life could develop after that. There are also studies that show that for certain kinds of M stars, possibly the very late M stars, that they're not as active as we once thought all M stars are. So we have a lot to learn.
Wow.
And they're watching it. Even, and I guess they're watching it for flares now, but it's a very faint star. I'm not watching it.
It's about 18th magnitude.
Yeah.
It's in the southern hemisphere, so you would have a lot of issues there.
Just one last question for me. Are you planning on looking at all of Kepler stars for duplicity, or you just take a sample of them?
Well, we've looked at, like I say, about 900 of the 4,000 stars with planet candidates. We certainly will never look at all 170,000 stars. That would take us
The one with planets.
Right. So we've now mostly moved on to observing and looking at stars that were detected by K2. They tend to be closer to the Earth, which gives us a better resolution, and they tend to be brighter, which gives us better signal noise. And we'll try to do a large sample of those. And then the next mission, which is called TESS, is going to look for transits over the entire sky. So it will find many, many bright stars with transit candidates anyway, and in a few years we'll move on to observing those stars.
Very cool.
Okay, one quick comment. You commented you probably can't have a talk about Kepler without talking about exoplanets. Actually, I got a bit interested in gamma Dorada stars and close binary systems, radio pulsators.
Right.
And so actually, I can't think of his name, down at San Diego State, that had a paper, and I think you're actually a co-I on it, about KOI 54. So
KOI 54, yeah.
we had a talk on that here. So
That's a fabulous star.
yes.
And that's the prototype of a bunch of stars called the heartbeat star.
Yes.
Yeah.
So
Yeah.
actually, we did have a talk here with Kepler data, but no mention of exoplanets.
Yep. Yeah.
Okay, if there's nothing else, please join me in thanking Dr. Steve Howell one more time.
Great.
Steve, thank
All
you
right.
so much.
Enjoy the rest of your meeting.
And, well, this isn't the meeting, we just get together for the lecture series. This is different from our meeting, so.
Oh, excellent. Enjoy what you're doing now. Go look at the sky.
Yeah,
And if you're ever in the Southern California, want to come up to Big Bear, you're more than welcome. And if you ever want to see the observatory here, stop on by.
Great. Thanks a lot. All right. See you guys.
Bye.
Good night.
Bye. Good night.